Symmetries in your model is a kind of enemy for the CP modeler. Why it's an enemy? Because it will map non-solution to non-solution and solutions to solutions. But you should avoid them because exploring symmetrical search space is really a waste of time. So the goal there is to try to remove as much as possible the symmetries of your problem and also to detect them. So the first type of symmetry that I will explain is what we call the value symmetries. So we have a bijunction function sigma here that will do the mapping from non-solution to non-solution and from solution to solution. Okay, and so this mapping function in terms of value symmetry, you apply it on the values themselves. So x1 takes the value a1, xn takes the values an. So if this is a solution, then once you have applied the mapping and apply the mapping on each of the values there of your solution, you still get a solution. And that's also true for non-solution. So if this is a non-solution, by applying the mapping, you also have something that is still not a solution. Okay, we call that the value symmetry, such a bijection function mapping sigma. Let's come back to the bin packing problem to make sure that we have an example of a value symmetry. So clearly, what we can do in terms of mapping here function to try to generate symmetries is simply a mapping function that will exchange completely two different bins. So let's take these two bins, for instance. I exchange them, I still have a solution to my bin packing problem because they have exactly the same capacity. So if I decide to simply change the assignment, okay, so if I come back, so if instead of being assigned to this bin number 3, this one is assigned to bin, this item is assigned to bin number 2 instead, the same for that one, and while this one will go there, I still have a solution. We call that the value symmetry in this case, okay? And it's quite easy to come with the design of a bijunction in that case to prove that it's a value symmetry, okay? So how do we avoid these value symmetries? Because we do not want to explore symmetrical search space. One possibility, and it's quite easy to put in practice, is simply to add constraints. So I can, for instance, impose a total ordering on the bins, and I can do that on the load variables. I can say, for instance, that the load of bin 0 is less than or equal to the load of bin 1, less than or equal to load bin 2, and so on. Okay. So if I impose this constraint, clearly this is not a solution anymore because I need to have the smallest load for a bin in the first bin. So I will need to exchange these two ones. Okay. I need to exchange these two ones. But as you can see, the bin 1, 2, 3, 4 still have the same load, so they can still be flipped. And so this kind of symmetric constraint will not break the symmetry completely in case of ties, as it's the case in this instance. So instead of that, what you can do, and that's a little bit better for the bin packing problem, is that you can impose a lexicographic ordering, okay, that I represent with this constraint that is not implemented. Okay, that's pseudocode there. So I can impose that this vector of bin number j is strictly less than or equal to the bin j plus 1. Okay, and this is a special type of constraint that we call the lexicographic ordering constraint. And if you're interested into a lexicographic constraint, you can read this paper that explains lexicographic constraint. Okay, so that's not available in MiniCP. Okay, and it's also not part of the project that you need to implement, but it exists in constraint programming. If you would like to break the symmetries a little bit better, that's what I have done before with simply ordering, putting an ordering on the load variable there. It's better to do it with a lexicographic constraint. Okay, that's it for the value symmetries. We have another type of symmetry for the bin packing problem. That's the variable symmetries. In that case, the bijection function, you will apply them on the indices of the variables. Okay, so you simply exchange the variables and not the values anymore. The value will stay the same. Okay, but you flip the variables. You change the variables. So what are the variable symmetries in this problem? Clearly, if you took two variables there, for instance, this variable and this variable, if you exchange the two variables, you still have a solution. So you take two items with the same weight, you flip the variables, and you still have a solution. That's a variable symmetry in the bin packing problem. And to break these value symmetries, we can use the same technique as before. We can simply impose constraints, and we will put here less than constraints between the variables that correspond to exactly the same items in terms of height or weight. So all the green items should be placed in that order, all the blue items in that order, and so on and so on. So you know that this one, exactly this one, should be placed in a bin that is before equal to the bin decided for that one, before equal to the bin. And you can convince yourself that you do not remove any feasible solution. Well, you remove solutions, but if there was a feasible solution to your problem, there still will be a feasible solution to your problem after adding this constraint. Okay, that's the goal of variable symmetry. You remove solutions, but you have the guarantee that if one solution exists, it still exists after adding these constraints. So there is a drawback of breaking when you break symmetries by adding constraints. Sometimes it's useful, sometimes you will realize that it's not. And it's quite counterintuitive. So I need to explain a little bit this phenomenon. So assume that without symmetry, that's the search tree that you will explore. And the first solution that you will find is this one. Okay. But these are all the solutions feasible to your problem. Assume that this solution is symmetrical to this one. When you will add constraints to break the symmetries, maybe this one will not longer be a solution to your problem. It will disappear. And as a consequence, the solution that you will discover first might be this one instead of this one. And so you will spend quite a while exploring the search tree before reaching the first feasible solution to your problem. Okay? And so simply because you have added a new constraint to your problem, you spend more time. You might spend, it's not guaranteed, it might help, but in some situation it doesn't help, and you will realize that you will take more time to discover the first feasible solution because there is a kind of bad interaction between the heuristic and the search. So the challenge now is, can we find a technique to break the value symmetries or the variable symmetries so that the first solution remain exactly the same as before? And the answer is yes, it's possible to do that, but we need to do it in a dynamic way during the search. So during the search, we will try to avoid symmetrical search spaces. Okay, and we'll implement a dedicated search for that. So the search for the bin packing problem is this one. You pick one item, which is not yet packed inside one of the bin, and the branches that you will create is one alternative for each of the bin. Okay, this is exactly what I'm doing there. I find the first variable of x that is not yet bound. Let's say that it's this one that is picked. Okay, if I can find none of the items that is not yet fixed, then I will simply return empty there to tell the search that we have a solution. Okay, otherwise we have this variable that corresponds, that's the item that we need to place, and I will create a list of branches, and I will try to consider every possible bin if that bin is still part of the domain of the item, and I will create a branch just to fix this variable of the item to this specific bin that I'm currently iterating on. And then here I return all the possible alternatives. So really what I'm creating there is all these different branches. Okay, so in that case I've created 1, 2, 3, 4, 5 different branches under this specific search node. But you can realize that some of the branches are symmetrical, right? And especially these three. Let's look at these three. If you look at these three, you see that they are completely empty at that point. And so trying to explore this alternative or this alternative or this alternative is a little bit useless. Considering only one empty bin is enough because this one is symmetrical to that one at this specific node, and this one is also symmetrical to that one at this specific node. So I will avoid these two branches. I will try to avoid them. And to do that, I will compute here the maximum bin that is used so far. Okay, so in that case, if that's the bin 0, 1, the maximum bin here is the bin number 1. And what I will do here is that I will create a number of branches maximum up to the maximum bin plus 1. So I will only consider these branches. Okay, and I will avoid trying to place this item with a weight of 4 in these two specific bins because they have exactly the same load. So I will not branch on them. If I do that, I will dynamically break most of the value symmetries of my problem, of my bin packing problem. So that's a very powerful technique, because also by doing that, you do not delete your first feasible solution. So you have the guarantee to have the best of the two worlds. You avoid symmetrical spaces, search spaces, but you also find equally fast the first feasible solution. So let's summarize a little bit the technique that we have seen to break symmetries. You can add constraints. That's static symmetry breaking techniques. You can add constraints to your model. The drawback of that is that you will remove solutions, and as a consequence, you might take a little bit longer to find your first feasible solution. If you want to avoid this bad situation, you can also try to break symmetries by using a dedicated search and dynamically avoid some of the branches that you consider as equivalent.